Question 3. A scientist is asked to find the rates of decomposition of aromatic diazonium compound and determines the order of the reaction with respect to the aromatic diazonium compound. And part A is the mostly preparations of a solution, a salt solution. Okay, so now scientist is given 1.02 gram of the aromatic diazonium compound in a 50 cm3 pickle. Describe the step the scientist would take to make 100 cm3 standard solutions containing 1.02 gram of this compound. Okay, this one you must include the name and capacity of apparatus that use and list out the steps. Okay, so first please look at this the preparation, the diagram. Okay, initially is 1.02 gram of the salt inside the pickle. So the first step, we must add a small amount of water to dissolve this salt. After that, once it's formed solutions, aqueous solution, we're going to pour this solution into the volumetric flask, and we have to wash a few times and pour the washing into the same flask. After that, we try to top up, okay, to the mark, means use the distilled water, top up the solutions to the mark, normally is on the neck. So after that, the solutions is prepared. This is how we prepare the solution. Okay, so this one is the full answers, okay, for this preparation. Add small amount of distilled water. This is first step. Add small amount of distilled water to the 50 cm3 pickle to dissolve the aromatic diazonium compound. Okay, second, transfer the solution and the washing using a funnel into the 100 cm3 volumetric flask. You must mention volume and what is the type of apparatus. Okay, last step. Make up to the calibration mark with distilled water, then invert and shake to homogenize the solution. So the solutions already prepared. Yeah. Part B. Benzene diazonium chloride and is aromatic diazonium compound. It decomposes in solution to produce phenol and nitrogen gas. So this one you learn it in the organic chemistry. If you not really learn it, please do some study and revision. So you in the organic chemistry, this is a reaction. Whenever the benzene diazonium salt, right, is get warm or at higher temperature, it will produce the phenol and the gas, nitrogen gas. If you don't know how the reaction looks like, it's okay, because in this question it's not really asked how. So what you need to know is just the decomposition release gas, and you need to measure the gas here. Okay, now the scientists warm 50 cm3 of solution to 50 degrees C and record the volume of nitrogen gas produced at different time during the decomposition. So means it's the volume collection at different times, so we can get the rate. Okay, part 1. Identify the piece of apparatus that would be used to maintain the temperature of the solution. Very easy. Normally we maintain the temperature of solution using thermostatically controlled water bath means the water bath with thermostat, so we can control the temperatures of the water bath easily, right? Okay, this is the standard answer. Okay, part 2, identify the dependence variable. So it depends on the temperatures that we use. Of course, higher temperature is produce more gas or larger volume at different times. Okay, so therefore the dependence variable, it will be volume of the nitrogen gas that produce. Okay, part 3, suggest why the scientist does not monitor the reactions by measuring the mass loss. Yeah, because it's produced nitrogen gas, it must be a mass loss. Okay, but it's actually impossible because we cannot really weight the apparatus while the temperature is maintained in water bath. Okay, let's say when they ask you to draw the setup, this is how it looks like. So we put the solutions into the special flask, right? Okay, after that, connect this flask with the gas range, so we can collect the nitrogen gas, okay, at different time. Means we just read at the gas range volume at different time, so we can get the rate and the orders later, right? And of course we have to immerse this solution, this salt solution, in the temperature control water bath, so then we can get the gas accordingly. Okay, again, it is not possible to weight the apparatus because all inside water now, cannot measure. So means we cannot really put a balance in the water bath, isn't it? Okay, part C. Table 3.1 shows the results of the experiment. So we have the different time, and this is a final, means the reaction done, and the volume at different time, volume that produced at different time. Of course, it's going to be more and more and more, right? So it is added up from time to time. Okay, after that you have to do this part, use the final volume minus the VT. Okay, so the first one of course is 57.2 minus 0, so you get back the same value. So second, you use 57.2 minus the 17.3, you get this. Do the same calculation, then you can get all these values, right? Okay, so we discuss part by part. Okay, part 1 already done, complete the table, you should get all this value. Part 2, plot a graph in the figure 3.1 to show the relations. Must draw a curved line of best fit through the plotted points. Okay, so this is okay, this one is what I did. I think you can do much better than mine. So after you plot, make sure the curved line pass through as many plots as possible, and you must circle the anomalous point. Okay, so plot all the values correctly, 1 mark. Okay, best fit, 1 mark, right? So just 2 marks for the graphs. Okay, so this one we discuss later. Okay, so the graph done already. Part 3, circle 1 point of graph considered as the anomalous. So this one already done. So it's the point at for my one is a point at 21 minutes, right? Okay, this is the anomalous. Okay, so after that, okay, part 4, suggest one reason to explain the anomalous point that you have circled. Assume no error made in the measurement of volume. It depends on where is it, above the line or below the line, because my one is above the line. Okay, so what you need to really consider is, okay, is at 21 minutes, it's supposed to be around this point here. So the volume now is larger than expected. So why the volume is larger than expected means the volume difference. It because of what? So the reason is the measurement of volume was made before the time recorded in the result table. Means the student or the scientist make the measurement before 21 minutes. Means before that. Why? Okay. Again, if this one is the abnormalous point, and this value is higher than expected from the graph we discussed just now. Why is higher than expected? Okay, because actually the VT means this one, it should be larger. When it's larger, 55.2 minus a larger volume, you get a smaller one. Because this value actually it should be smaller. It's expected to be smaller than 14.6. It because it's measured earlier than 21 minutes, the volume here is actually lesser. So 57.2 minus a lesser volume, you get a larger volume here. So that's why it's too early, okay, to make the measurement. Okay, the VT it should be larger actually, larger than this. Right? So I hope you understand what I try to tell you and try to digest it. Okay, so this is a graph. You can do much better than me again, right? So this is the part that quite challenging. You have to use the graph to identify or determine the half-lives. Use your graph to find the first two successive half-lives for this reaction. Of course, the half-life is better to start from the this value. So for this this one is the volume at 0 minute, right? Volume. So half-life means when it's reduced to half. So we get one coordinate here, and we try to find another coordinate when the volume is half. So volume half, which means is around 28.6. Okay, so half of this volume. So from my graph, I get roughly around 28.6 like that. Okay, so my one, 28.6. So it's about so it's about 9.8 minutes, right? 9.8 minutes. So for my one, the second coordinate is this 9.8. Okay, and the volume is 28.6. So we must use 57.2 and 28.6, right? So because the volume reduced half, that's why we choose we use these two coordinates. Okay, this one and this one. Try to find the time, okay, from the graphs. So the half-life obviously is 9.8 from my graph, and the second half-life, then we just continue. So we use the same coordinate here, 9.8 and 28.6. So Now 28.6 need to be half. So 28.6 half means 14.3. 14.3, my graph is about like that. Okay, 14. Okay, so it's around 14.3 is around this, right? Okay, so 14.3, my one is around here. 14 point around here. So this part. So 14.3 is roughly here. Okay, my one is 14.3 is 90 minutes, right? So from the graph, so it's about 90 minutes. Okay, so from 28.6 to 14.3, so it's about 19 minutes. Okay, so means the second half life is going to be 19 minus 9.8, so get 9.2. So this is second half life. Okay, the last part. Use your answer to the C part 5 to state the orders of the reaction with respect to the benzene diazonium chloride. Okay, so because the half-life is quite close, about 9 point something minutes, so we can say that it's a constant. So it's a first order, and explanation is just half-life, they are constant. Right. Okay, that's all. Thank you.